Hey everybody, today we're going to cover a bit of a review session. This is everything you needed prior to Algebra. Now this is an Algebra 2 playlist. This is for my Algebra 2 class primarily. But Algebra 2 is just a continuation of Algebra 1. Plus we'll throw in trig later on. But for now, before we really dive into the Algebra 2 stuff, I would be loath to not first cover some arithmetic stuff, and then introduce algebra, then cover some Algebra 1 stuff. Not all, just a few key things. So for this first video for our class, I'm going to go all the way back to arithmetic, and I'm actually going to start at the fundamental theory, the fundamental theorem of arithmetic. The fundamental theorem of arithmetic. I'm going to give you a few examples. For those of y'all who don't have me as a teacher, I like to teach by examples. But let me explain to you the abstract. The fundamental theorem of arithmetic has to do with prime numbers. It states that any whole number can be broken down into factors of prime numbers. For example, give you a few easy ones. 8 is really equal to, well, before I even start to give you examples, let's make sure that we know what primes are. 2, 3, 4, 5, 7, 8, 9, 10, 11, 13, 15, 16, 17, 19, 23, 24, 25, 26, 27, 28, 29. The list goes on. There's an infinite number of primes, and there's no pattern that they follow. It's just that they're not divisible by anything other than 1 and themselves. So 3 is divisible by 1 times 3. And the same can be said for all of these. They're all only divisible by 1 or by themselves when it comes to whole numbers. So when it comes to these primes, there's an infinite number of them. Their pattern has not been established, if there even is one. There's actually a $1 million reward for anyone who can find a pattern in the primes. It has to do with encryption. The reason why it's a valuable question. It's also a valuable question in mathematics, but let's not get too into the weeds with prime numbers, as fun as they are. We have prime numbers. Let me give you an example of what the fundamental theorem of arithmetic covers. These are prime numbers, right? Infinite set. But anything can be broken down into its prime factors. Let me show you what I'm talking about. 96 is really 2 times 48. 48 is really 2 times 24. 24 is really 2 times 12. Whoops, don't want to circle 12 because if you guys notice, I'm only circling the primes. So 24 is 2 times 12. 12 is 3 times 4. 4 is 2 times 2. Forgot to circle that. So what we have is 2 times 2, 4, times 3, 12, times 2, 24, times 2, 48, times 2, 96. Technically, 96 is 2 times 2 times 3 times 2 times 2 times 2. Or let's see, 1, 2, 3, 4, 5. It's 2 times 2 times 2 times 2 times 2. 5 of those 2's there multiplied by themselves times 3. You'll hear me say this a lot in these videos. Mathematicians are generally lazy. We like to minimize the work we have to do. So this actually simplifies down to 2 to the 5th, the smaller number, the smaller prime first, times 3 to the 1. So 96 can be broken down into its prime factors of 2 to the 5th power times 3. I'll do one more example. 40. 40 breaks down into, let's do it differently. Instead of doing 2 times 20, which it does, but I kind of want to take a shortcut here. I'm going to do 4 times 10. Neither of those are prime numbers, but that's okay. It'll end up the same for me. 4 breaks down into 2 times 2. 10 breaks down into 2 times 5. And apparently that's it. 2 times 2 times 2 times 5, or 2 times 2 times 2 times 5, is going to equal 40. So just a couple of examples of what the fundamental theorem of arithmetic sets out to accomplish. Other things that you're going to need from arithmetic moving forward. You'll have to understand how to evaluate using Pemdas. You will have to learn how to evaluate using Pemdas, where the P is parentheses, or these bracket thingies. The E is exponents, so x squared, or 5 to the 9th, or y to the 4th, or z to the 10th. The exponent is the power to which those different numbers or variables are raised. Next, you have multiplication. We don't really use the x anymore for multiplication, actually. As we move into algebra, we stop writing x for multiply. We generally write a dot between two numbers, or we put the two numbers in parentheses like that to symbolize a multiplication. And then for division, we won't really see that symbol too often. I guess we will with fractions, but we'll generally see either this or just a division symbol with a numerator and or a denominator present. Lastly, you do addition and subtraction. This is the order in which you approach a problem. For example, I like those examples. For example, 2 minus 3 squared plus 7, all of that divided by 2. Now, again, mathematicians are lazy. Generally speaking, you see this fraction line, just assume that everything on top and everything on bottom is one thing. So that 2 is dividing that whole thing. That whole thing. So if we are to evaluate this, we have to go down this list. First parentheses, then exponents, then multiplication and division. Lastly, addition and subtraction. So we see a parentheses here. There's nothing to be done down there. Let's look at the top one. We see a parentheses here. Let's look inside. Inside this, there is another parentheses. Inside that, there is no parentheses. So we go to the innermost parentheses, and we do that first. 2 minus 3. 2 minus 3. That's, for those of y'all who don't know, 2 minus 3, that is negative 1. We're going to square that. We're going to add 7. Then we're going to divide by 2. Okay. Well, this is really the same thing as saying negative 1 times negative 1. That's just 1. Negative 1 times negative 1 is 1. So we're saying 1 plus 7 divided by 2. 1 plus 7 is actually 8. So 8 divided by 2 is 4. So you'll need to be able to operate with Pemdas, with the order of operations. Feel free to Google that or find another YouTuber who covers this much better and in more depth than I do. But not only will we need Pemdas, when I start to introduce Algebra 1, we're going to see the order of operations taken somewhat in the opposite order when we're solving for variables. That's coming up ahead. For now, I just want us to focus on that fundamental theorem of arithmetic, the order of operations traditionally, and lastly, fractions. We are going to be dealing with fractions. We're going to be dealing with fractions a lot in algebra, and I'll explain why. I don't know if I'll explain why now, later, or in the next video, but we will be working a lot with fractions. So let's go over a few of the old fraction rules. We are allowed to multiply two fractions if they have the same denominator. So if they both have a denominator of 5, we can add or subtract those two fractions. Let's say you got 4/5 plus 7/5. Well, the denominator stays the same, 5, and then you add the numerators. It's going to be 11/5. If you do not have the same denominator, you have two fractions. Let's say you have 2/3 plus 8/9, and you're trying to add those two together. Well, you got to get that denominator to be the same as that one, or that denominator to be the same as that one. We now manipulate this, and we're going to be manipulating a lot of algebraic terms by 1. We're going to be multiplying a lot of algebraic terms by 1. Now, arithmetic is multiplication, division, subtraction, addition, but especially with the multiplication, a particular property of multiplication is any number times 1 is itself. X times 1 is X. 5 times 1 is 5. 11 times 1 is 11. Negative 17.5 times 1 is negative 17.5. Negative 17.5. Any number multiplied by 1 is just itself. One more property, this one is from division. Any number divided by itself is 1. 17.5 divided by 17.5 is 1. 1,000,000 divided by 1,000,000 is 1. Those are two properties from arithmetic that will be present all over algebra. So remember, any number divided by itself is 1. 1 times any number is just that number, unchanged. Let's come back to our problem then. When we're adding fractions or subtracting fractions with different denominators, we have to get that denominator to be the same. So let's multiply this by 1. 1 doesn't change a number, right? We're allowed to multiply by 1, but 1 can also be expressed by a number divided by itself. Now, fractional multiplication, that one's a little bit easier in my opinion than fractional addition and subtraction. Fractional multiplication, multiply the numerators, multiply the denominators, and you're good to go. It'll be 6/9 plus 8/9. Now we just go back and we add those numerators. We're going to have 14/9 as our final answer. The same can be said for subtraction problems. 2/5 minus 1/10. Let's multiply this by 5, divided by 5, aka we're multiplying by 1, because 5 divided by 5 is just 1. We're allowed to multiply by 1. It doesn't change the number. That'll get us, oh wait, wrong one. I need the denominators to be the same, and 5 times 2 is 10. So I need to actually divide by 2 and multiply the numerator by 2. So I got to multiply by 2/2. I got to multiply by 1 here. So I'm going to get 4/10 minus 1/10, or just 3/10. Last bit of fractions. And this tends to confuse people. Fractions have a special kind of property when you divide them. Now, multiplication, as we just went over, isn't too crazy. You multiply the numerators, You multiply the denominators. That's your answer. But what about division? Let's say you got 2/7 divided by 9/3. I'm not going to go into the theory. I'm just going to go through this real quick. Whenever you see a division symbol like that, don't panic. All you got to do is take that 2/7 and instead of dividing it by 9/3, flip it, multiply it by the reciprocal or the flipped version of this, multiply it by 3/9. Multiply it by 3/9. That'll get you 6. 9 times 7, 63. That'll get you 6/63, which will simplify down to 21. 21, sorry. 21/2. The reason why it simplifies, I don't want to get too far into the weeds, but the reason why it simplifies down to from 6/63 to 2/21 is because 6/63 is really 3 times 2, because 3 times 2 is 6. 3 times 2/63, which is really 3 times 21. So we got 3 times 21 on the bottom, 3 times 2 on the top. But we have this 3 divided by 3. So the 3 divided by 3 is just 1. It doesn't change anything. It can be, quote unquote, canceled out, if you will. And it'll just leave us with 2/21. Those are the key things that you will need from pre-algebra. In the next video, I'm going to introduce algebra and hit on a few key components. But yeah, thanks. Welcome to the course. Hopefully this was an interesting review. If you need any help on fractions, fractional addition and subtraction, fractional multiplication and division, again, Google a YouTuber. Google a math YouTuber. They will have so many videos out there available for y'all at a much higher production end than what I'm capable of by much more competent people. So please do that. And yeah, thanks for tuning in. Appreciate you guys. Cheers.